Hello, we want to discuss in this lecture trigonometric functions and complex numbers. We'll start with trigonometric functions in this particular subsection for today's lecture, and then we'll go on to relate those to complex numbers, which is a bit of a review of what we've done before. Now, trigonometric functions are important in engineering, physics, and mathematics. We use them a lot. One of the reasons that I'm going over this review is that a lot of times in a high school math class and even in some university math classes, the trig functions kind of get left to the end of the class. If there's not time, people don't go over them. So because a lot of people don't take a formal trigonometry class, a lot of people have some holes here. So we'll just give you what you need for success in future engineering classes and to review you for future math classes. There are some decent references and resources that I've posted here. Khan Academy is always good. There's a math open reference. There's a Wikipedia site that's pretty good the last time I checked it. So a couple of different sites, and also I've pulled from those sites for some of the photos in this slide presentation. Now, in trigonometry, basically there are relationships within a right triangle, which of course you all remember a right triangle has one of its sides equal to 90 degrees. These relationships exist between the angles in the triangle and the lengths of the sides. And the most common of these relationships are the sine, the cosine, and the tangent. As I said before, these functions are widely used in engineering and physics. And initially, we're just going to review trigonometric functions with respect to triangles, and then we'll talk about how we use them in AC voltages and signal processing in electrical engineering. So here's an illustration of a right triangle. It has angles A, B, and C. And then notice that the side of the triangle opposite the angle A is labeled with a lowercase a. So because the angles A and B are both less than 90 degrees, they're referred to as acute angles. The angle C in this case, the way I have my labeling, is the 90-degree angle. So when we talk about things with respect to angle A, we talk about the opposite side of the triangle, which is illustrated here with the lowercase a, and we talk about the adjacent side, which is illustrated here with the lowercase b. And then the hypotenuse, obviously, is always the side of the triangle that's opposite the right angle. So if the angle A is given, then we could basically know, relative to a scaling factor of the length of the sides, what the lengths of the sides are. So basically, if we have one angle defined in this triangle, then from geometry and trigonometry, we can know all the other angles, and we can know the ratio of the lengths of the sides. So these are the definitions of the trig function. We're referring here to angle A, and they're given here. I'm sure you have seen all of them before. In engineering and physics, we overwhelmingly use the first three more. In electrical engineering, we typically, whenever possible, use the cosine function. All right, this is also a table really just here for your reference to review some useful trig identities. I'm not going to test you over memorization of these, just they're here to put kind of a reference of everything in one place. One thing I want to point out are, first of all, these first two relationships between the sine of a negative angle is basically equal to negative sine of that angle. The cosine of a negative angle is equal to cosine of that angle. These show up a lot, so if you had forgotten these, then that's just a good reference for you. Another useful one is that if k is an integer, if you look at these expressions in the second group here for sine and cosine, if k is an integer here, then the sine of x plus 2 times any integer multiple of pi is equal to the sine of x. Same with cosine. Actually, same with all of the trig functions other than tangent and cotangent, where you don't need the 2. So basically, if we add an even integer multiple of pi to sine or cosine, we're basically the same angle. That's because 2 pi radians is 1 full circular revolution, and so, and you could actually prove that if you wanted to. You could prove that using the sum rule, where you could let y be 2k pi, where k is an integer, and then you would find that basically you can prove these expressions. So that's that. Then, if we go to the next slide, you can see listed here are some possible applications. In physics, the trig functions are commonly used to describe motions and forces. It's pretty useful in civil and mechanical engineering because a lot of times you want to resolve problems into individual x and y dimensions. In electrical engineering, trig functions are used to describe sinusoidal oscillations present in AC voltages and electromagnetic radiation. These are often referred to as sinusoids or sinusoidal functions. And in mechanical engineering, they're often used to represent vibrations and mechanical waves. So that brings us to the discussion of the unit circle, because in electrical engineering, a lot of times voltages or signals will vary sinusoidally. And so what do we mean when we say that? And the easiest way to start with understanding what we mean to say when we say that is to look at the unit circle. So the unit circle has a radius of 1. It's centered on the xy axis, and the angle is defined in the counterclockwise direction from the x-axis. So here we have basically a point on the unit circle, point A. Because the hypotenuse has a length of 1, then the vertical dimension turns out to be the sine of theta. The horizontal dimension turns out to be the cosine of theta when the angle is theta, and the length of the hypotenuse is 1. Now, the reason that this is a useful visualization tool is that you can easily see here what we just discussed in the trig identities, that if we now, from point A, do a full rotation around the entire circle, we end up at point A again. So this sort of proves that the sine of theta and the cosine of theta are the same, whether we just make a theta rotation or whether we go another 2 pi or a second 2 pi, we still end up at point A. So the unit circle is primarily useful for visualizing things that vary sinusoidally in time, because as time goes with the cosine function, if the angle varies with time, you're basically rotating around this unit circle in position.